All right, welcome back. So this is part two of the three-part peer review workshop series. So in part one, we looked at pretty basic operations, things like loading state, loading files, save state, axis grid, and when we dealt with steady state data. So for this part, part two, we're going to be dealing with transient data involving time step. We're gonna look into point data and also some new filters or newer filters that we didn't touch on in part one, things like vector plots and also Q-criterion contours. And I'll also kind of talk about exporting as VTK and also CSV. So quite often we'll have to do other post-processing in things like say Python, etc. Now, before we jump in, I'm just going to explain a little on basically the example case, the data that is attached, just to kind of give us some context. So, it's modeling something called a synthetic jet actuator, SJA. The way it works is kind of similar to your human lungs. There is a cavity with a diaphragm that expands or contracts, and then during the ingestion cycle, the volume in the cavity increases, draws the air in, and then during expulsion, it squeezes it back out, forming a vortex ring. Depending on the Reynolds number, it can either be laminar, so giving us a little vortex ring, or it's going to come out turbulent. Now, the example I included today is actually based on the one on the right, but rather than having, let's say, hundreds of samples, I only include five because each time step is around 300 megabyte. Um, so if I include all 100, it will be impressive, but it's gonna take out quite a bit of your hard drive. Okay, so first thing first, we're gonna talk a little bit about ParaView settings. So if you go onto your upper left under Edit, all the way down, there's a little gear settings, and as usual, you want to toggle this gear button to make sure you have advanced on. It just shows you a lot of hidden settings. Um, the reason why I didn't dive into this in the first tutorial or workshop, the first part, is that I think it's a good idea to kind of play around with the software a little bit first, and then so that when you kind of read over this, it gives a lot more context. A couple of the ones that are worth highlighting is autosave on exit and autosave. Now, these are good, but sometimes when you have apply a wrong filter, like an illegal filter, and then crash the software, you don't want it to get stuck on there. So you can turn this on, but personally, I still have a manual save state. You can also do crash recovery, but I tend to like my own version control instead. And now what I want to talk about is the GUI font. So by default, it does not have it enabled. And depending on your computer, it might have a different font setting where things might be a lot bigger. So I tend to like having it at the minimum. Auto apply is also another setting you can consider turning on, but for myself, usually the default filter doesn't give me the setting I want, so I have to adjust it anyway. So I tend to like adjust everything and then just press the apply. Um, if you're doing some very precise like nanosecond simulation, you might want to change the precision for the time, but then otherwise that's mostly it. Um, One thing I do want to mention, so personally I do prefer the 5.11 layout. Those are on the same font size. You can kind of see that we have more real estate in the middle. And if I bring out the color map editor, it doesn't really go in anymore. Whereas 5.11, I get a lot more room in the middle. Um, The only way I figure out how to change this is by changing the zoom for the entire Windows system, and the setting applies to all software, which I don't want it. It's too small. Um, so maybe this is just a quirk because I'm using Windows 10 instead of Windows 11. Uh, but you can kind of try out a couple of different versions. I know as of right now, 6.2 is the latest version. But I started this when it was 6.1, so I'm not going to re-download it. Okay, now let's open our Path2's folder. So I'm already added to the favorite. Again, you also have recent, otherwise you might have to dig this up depending on where you downloaded it. Um, so one of the things I do want to mention, sometimes depending on how the file format are saved, uh, ParaView can detect it as a time series. So in this case, it's actually in a collapsible. This also applies to VTK later on. Okay. So if we go into the middle upper under time, there's a drop down, and then we can see that there are 5 time steps between 0.1 second to 0.11. Now, similar to Python, so it starts at 0 in terms of integer. So then it goes to the first time step, second, and then so it says max is 4, but technically we have 5 time steps. And later on, when we export animations, we have to take that into consideration if you don't want to export everything. So first thing we're going to do is look at how to generate Q-criterion contours animation. Um, in part 1, most of the filters we've used are basically kind of attached for us on the hotbars, but you can also find the same thing under the filter tab. Now, if you go into alphabetical, it shows you everything. For some reason, the resolution glitches out some of it, but you can also manually search it if you know what they're called. So, for example, if I want to get a contour, and it shows up. But right now, we're gonna get gradient. Now, when you apply the gradient filter, you have to select the array. You can get pressure array, but I tend to use velocity for unit velocity for the Q criterion contours. We're gonna unclick the gradient. You can keep it if you want to look at the components, but instead I'm gonna click compute vorticity and compute Q criterion. I'm just gonna do a quick slice at the mid span just to show what we've computed. So it gives us 2 new fields, omega, vorticity, and then there's also Q criterion. Now, for Q criterion, we don't usually present it 2D like this. Instead, what we do is apply a contour filter that I talked about in the first part. So click on a gradient and click on the contour, adjust to Q criterion, and if you scroll down, you're gonna input a isosurface threshold. Now, the actual value you want to put in changes quite drastically from case to case, and even the similar flow at different Reynolds number, your Q criterion contour, the threshold will change. It is mostly a trial and error until you get something that looks good. But you can also look at literature, and then usually the publication they'll tell you the threshold or a normalized threshold of how they presented it. Now, when we plot Q criterion contours, we took a threshold or a contour, so it's just going to give us the same color. And so I tend to like coloring it by omega, usually either omega Z or omega X. And we also have to manually adjust this range. Now, um, if we look at here, we can kind of see that it's quite blocky. The reason is that CFD, the data or the computation is performed, and for the cell center, so the whole cell, each of these hex has its own value, and it can change quite drastically from one cell to the other. Now, um, this is realistic because this is basically what's computed, but quite often we want to use point data instead. That smooths it out. Now, to do that, we have to go back to our main case that we loaded, kind of close to the top. One of the first boxes you can tick is create cell to point filter data. Now, before this, all we've loaded, all we have are cell data. And once I click that, what ParaView does is that read the cell data, but it also interpolates it and giving us point data. So it goes from these box to those cells. And if we look at the mid-span slice, right here, let's look at the pressure field. When it's a point, or sorry, in a cell format, each cell has its own value. So it's quite blocky. But when you change it to point data, it basically blends it out. It kind of smoothens it. Now, accordingly, we want to upgrade our gradient or update it to go from calculating based on cell values to point values. What this then does is that it gives us a way smoother contours, and also the omega coloring is going to be smoother. And voila. So even though we're not changing the mesh or anything, but it basically just blends it out. And one of the things I usually do when I'm testing out Q-criterion contours is kind of adjust it by a magnitude when I'm testing things out. And sometimes you might have to go up to pretty ridiculous numbers, and then finally we see something that actually resembles what a turbulent jet looks like. Now, the next thing we're going to look at is vectors, vector plots. Now, I've kind of reset the session, deleted some of the stuff in the pipeline just to keep it clean. Now, generally for vectors, we want to plot it on a 2D surface. You can try in 3D, but it gets quite messy. Now, so we've taken a slice here, and let's make the background sort of grayish. And to apply vectors, you want to highlight the slice and then click on Generate Glyphs. Now, by default, it should be using velocity field as a vector orientation array. For scaling, I tend to just turn it off. Um, and the reason is that, let's say if I do switch it back to scaling with velocity, um, usually what happens is some of the area, the velocity are inherently going to be stronger. And so you end up with kind of some of these monster arrow that are just way too big and is kind of impossible to kind of whack-a-mole it. So I just tend to stick with non-scaling and just give it a, or like not scale to the array, but instead like a uniform fixed scaling factor for all the vectors. And I tend to like making them into black arrows. Oop, the wrong one. Black arrow. Now, the vectors are 3D because our simulation is 3D. So what happens is that when we plot it on the slice, some of them gets hidden by the slice itself. So if you look, especially around here, some of the arrow gets hidden, and the reason is that it's basically going into the page. um, and then the arrow tip gets hidden from the render's point of view. So to get around that, you can either push the slice backward or you can pull the vectors forward, and it's under transforming, and voila. So now it's no longer being hidden. Now, you can change the seed density, so how many arrows to plot, um, and also the arrow size or the line width. Actually, no, that's something else. Oops, where is? Oh, I was fixing on the wrong filter. That's why. Okay, so under masking, this allows you to change the basically how many samples there are for the vector arrows. Um, Increasing it does populate it more, but at the same time, it also makes it quite almost chaotic, right? So one of the ways to get around this, rather than trying to play around with all these settings, every endpoint that never lines up, is to use a different filter called resample to image. Now, what this does is that it takes in your domain and then or your results, and then it resamples according to the dimensions you've given, or basically this is the number of cells. So if I show you how the original mesh looks like, we have a higher density at the jet exit, center lines, a fully structured mesh. Now, when we move into the resample, it becomes an actual uniform grid. Now, there are pros and cons to this. The pros is now everything is uniform, it's a lot smoother, but there are certain region where we originally had high cell count gets kind of downgraded. So now in the neck, we only have one cell in the width when we technically are supposed to have 30. And when we switch to resample image, we no longer have access to cell data because these are all interpolated. So we only have access to the interpolated point data. But if we apply the vectors, the glyphs onto the resample image now, and let's disable scaling, and let's change the color to black just to make it easier to look. And again, we want to pull it forward just so it's not being hidden by the page. And we can, and one last setting. Um, Here, so instead of manually changing the number of sample points, you can just ask it to plot on every point, and suddenly it's very organized, very uniform. And this is usually when I go into changing the arrow size, or you can also change the density. And let's say I'm going to reduce the resampled image density by 50%, and the arrow adjusts accordingly. But in this case, the reduction is so severe that the neck has straight up disappeared. Now, another problem is sometimes it ends up covering these void region that technically there's nothing there. And because we haven't given it a scaling, so it's still gonna have an arrow there, kind of a little thick. So to get around that, we can use a different filter called clip. Now, the way that clip works is that there's different clip type, and my favorite one is box. You can also use cylinder. And what the box does, as the name suggests, you almost taking a slice of like a box cutout from the domain. Now you're gonna have to manually define all this. Um, let's say 0.5, 1. Oop, that is way too wide. And let's hide the neck region. Now, the set direction is actually quite important, and for a couple of times I made mistakes where when I'm applying it on a plane surface, you have to make sure that your box covers the surface itself. So to be safe, I'm going to cover the entire domain. This is pretty overkill, but there's only one thickness or in a set direction since we took a slice, so it doesn't matter. But it does become quite important when you move on to 3D. Okay, so a few things I just did had to edit it out. Uh, when we apply new filters, basically the settings we did doesn't really get conserved, especially on operations like changing or basically moving the vector plots forward, just so it doesn't get clipped by the page. So it might be easier to just do it towards the end. I also made the background ambient, so I have to actually turn that to 1. It's something to do with open or ParaView's lighting box. So let's say we have a velocity, and if I just have it 0, 0 ambient, I'm gonna change the range from -1 to 1 because we're working reset. Technically, majority of these area are supposed to be basically white. Um, but then they don't come through, so you have to kind of drag ambient up to max to show that. And just to clean up, we're also going to make the background white. And we're also going to just replace it with just a surface. So it's pretty clean, but now we kind of want a border, all right? To get around that, there's a few ways, but the most convenient I found was just kind of copy and paste. So I'm going to reuse the same filter, um, but instead of plotting the velocity profile, and that's an odd color, I am just going to use the feature edges. Yep. So when you use the feature edges instead of just showing surface or surface edges, it gives it a very nice border around it, and then you can change the line width. Let's say I change it to 3, and voila, suddenly you have something that is reasonably presentable. Let's hide the XY axes, and then we can add the grid in. I already talked about the grid axes in tutorial 1 or the first video, so I'm not going to repeat it here, but you can easily toggle them on. You do have to change things to black. The other problem with the white background is, as we can see by default, our color bar is actually has white writings. So when I'm just looking at data or generating them, I don't tend to have a white background until I'm pretty close to something that is publication level. Now, the other trick you can also do, rather than trying to whack-a-mole and fix this color bar, is that as long as you save the state and you know the range of the color, let's say here I know the range is between -1 and 1, and if I change it to 25 levels, you don't have to actually drag this or relaunch this case to edit this. If you have the range, you can just open a blank case, lower dummy case, and then you can basically kind of work on the legend, and then you just screenshot them separately and then paste it to your PowerPoint or your Word document. Okay, so the next thing we're going to look at is Python calculator. It is basically a more powerful version of the basic calculator filter, um, but the basic calculator is easier to use. So quite often what I do is I basically do what I can with the basic calculator first, then I pull out the Python calculator. So as an example, what I'm going to do is to calculate the flow rate over basically the neck, the middle section of the neck. Now to do that, first of all, I'm going to take a slice. So now we just have part of the neck right in the middle to be precise. And then each cell is going to have its own UI. Now to calculate the flow rate, we're going to need two things. We're going to need the area and UI. And we already have the UI here, so the next thing we need is to find the area of each of the cell. And to calculate that is under cell size. Now it's very important that we apply the cell size filter on the slice itself. Otherwise, the area we get is going to be for the entire domain. I tend to deselect vertex count and the length. We don't really need volume because this is a 2D case. Oh, sorry, the slice itself is 2D, so I'm only keeping the area. Uh, Doing that, we have a new cell data being the area, and usually they're pretty small, depending on your mesh size. Now, we can calculate the flow rate locally for each cell. And we're going to use cell data because the area is a cell data variable. So just area times our, y, don't need the mac there. And I'm going to call it local v dot, local mass flow rate. And let's visualize it. So as we expect, it kind of changes from cell to cell, which makes sense. Now, to get the flow rate, we have to sum it up. Now, you can just export this, but you and do it in like PyCharm or Python. But we can also use the built-in Python calculator. So data, and what I'm going to do is sum our local v dot, and I'm going to call that sum v dot. Now, what that gave us is actually a summation of the flow rate. So let's hide everything. So the local flow rate changes from cell to cell, but their sum flow rate is actually sum over the entire plane. So it has one for every cell, but it's the same. And now what we do is that we can track it over different time steps. This is a great way to check if something is missing. It shouldn't be because mass conservation, but it's still good to check, or maybe we want to plot it. So to do that, we highlight the variable and then click this button here, extract selection over time. Always gives you a warning because you might be having, say, hundreds of time steps, and that can take a while. Okay, so that took, I guess, about 45 to 60 seconds. I'm also recording this whole thing, so it's going to be slower. Now, on the plot, let's only plot our flow rate, our sum v dot. So, this is pretty encouraging. It only looks like a triangle, but the way SGA works, they basically alternate between ingestion and expulsion. So the negative flow rate and the maximum expulsion rate, or they basically matches just in terms of one is positive, one is negative. If you have, let's say, 20 instead of 5 times step, it will look more like a sinusoidal wave of sort. You can also easily change this to a momentum by just doing UI times our area. There are other ways to use Python calculator, but the main restriction is that we don't have a lot of the comfortable features we have in calculator where we can basically select our scalar and vectors bound between different things easily. And since we already looked at plot selection over time, I might as well talk about placing probes and tracking it over time. Ideally, you do this in OpenFOAM with the probe feature. It is a lot better. It just gives you CSV. You can extract it every time step without having to writing the whole field. But you can still do this as part of the post-processing with this little button here, this little filter, sample data, and you manually define the location. So let's say I want to place it at the middle of the neck and give it a radius. I'm going to give it 1e minus 4. The neck has a diameter of 2 mil, so this should be quite small. Now let's open it up in a new tab. And similar to before, it only gives you, it gives you a point data. So this is interpolated. So if it glitches, if it has a bigger radius that encloses multiple cells, it will take an average from all the cells. Now, it's good to write the points, and let's say we want to track the velocity and pressure. And under the table, you want to highlight it, and then extract selection over time. I tend to like highlighting it first before clicking the filter, because otherwise, if you just click the filter directly, it will have a empty selection. Then you have to kind of manually select it again afterwards anyway. And similar to our flow rate, you just kind of have to wait a little depending on the speed of your computer hardware and also the how many time steps and the size of the mesh. So voila, another, I guess, 30 seconds ish. So let's get rid of this window. It's pretty similar to what I had before. And I've sort of mentioned this in the first part of the series. I don't tend to like doing too much work on the plotting within ParaView, especially for line plots. I find it more convenient to do these sort of line plots in Python afterwards. And so I tend to just export it as CSV. Well, that's a lot of variables. A couple of main ones. Let's say we want average velocities. And the most important one is time because we're writing temporal data. Now you can also output everything, but then your CSV is going to be massive. And depending on your application, you might not need max or medium. Um, and then you can just save it as CSV. So I can write this as probe 1. So we can look at a CSV, pretty clean. You can just load it into Python or PyCharm afterwards. Okay, next thing we're going to look at is export as VTK. It's actually pretty handy because quite often what happens with our computational domain is that it's massive. We kind of need a pretty wide domain from, let's say, geometries of interest. And those domains aren't really that important once the computations are done. Or let's say we've done a lot of calculations on some time average flow field. And that's, I should probably mention, that's another handy one under temporal statistics. You can press temporal statistics here now does is that instead of calculating the time average for like a point or a plane, we now have a flow field that is average for the entire domain. So in a sense, we only have to do that once and we have everything we need. This does take longer because then the averaging has to be done for quite a lot of things. Um, but this does not change with time because it's average. Now, let's say we have that temporal statistics and we want to save that because we might not want to always redo the computation, and in fact, we don't tend to want to. And the easiest is just through save data, and I'm gonna call it time average. Now, you can also choose what arrays to write. For example, if I don't care about standard deviation, I can unclick those. Maybe I don't care about the displacement. Uh, and maybe I only want to save the cell data. Now, so we saved it, and it's gonna look like that. So we named it time average, but it's kind of generated two things. So first of all, the PTM file, and then there's also a folder. And you need both components to relaunch it. So let's say we went away for a coffee break and we came back, and now we just want to look at the time average results. Then we can click on the VTM and we can choose to load everything, or let's say I only want to load our U average and P average. Might as well throw a new T in as well. And voila. It's going to have the variables. And you can see it's a lot faster because it's no longer applying any computation. So ideally what you do is you do the time average computation on a cluster, then you export it as VTM, and we'll talk about it more in the third part of the series. But if you run it in parallel, then sometimes they output the VTM parallel as well, which might be a little problematic if you're trying to look at it locally in serial. Another way you can do instead of exporting as VTM is that you can also export it as CSV. So here it's just a slice, but we can also export the data. So switching back to cell, we're given basically all the variables from the cell. Now since we have a VTM, so it doesn't have the cell location, only has the block name. So let's open the actual case again just to demonstrate that. So let's take a slice. And then let's look at that. Do point data, point displacement. The good thing with outputting the point data in this case is that you have a point location. Whereas with cell data, you only get a cell ID. I think there are ways to kind of dig it out from OpenFOAM, but it's quite a hassle, so I tend to just stick with point data if I'm trying to export it as CSV. And then you can do some pretty creative things in Python with the CSV because you can reconstruct it. You can also export things like Q-criterion contours and make some animations that might not be achievable within ParaView. Now, the last thing we're going to look at is Append Attribute. Um, Basically, it's a way for us to, let's say, combine two data sets to do some operations. Now, let's say we have our 3D geometry here, and we're going to take two different slices. And let's say I'm going to move that 0.01 in the negative direction. And then a second slice, but set to 0.01 instead. So basically, we have two planes here. Let's say I want to do a simple calculation of subtracting the U set between the two, and then see what's the difference. Now, if we just apply a calculator, it won't work because the calculator is basically pinned or inherits from the geometry above it, which is a slice. And so we're only going to have one set of variables. So we only have one UX or one U set. Now, to get around that, we can highlight both data set and then apply append attribute. And what that now does is that actually combine both data set into one. So we have U, and then you also have U input one, which is the second one that we've appended. Now, it's kind of a little buggy, as you can see. Wasn't sure if they patched it. It's still an issue. Maybe your version might be working. Um, so it loads the first one fine, but then the second one, I think something messed up. Uh, the best way to get around it, and this is not a guarantee, but I've kind of played around with it a little bit, is resample to image. This basically makes sure that the mesh are perfectly aligned. It can still sometimes get a little buggy, but this seems to be more consistent. At least it works sometimes. So where you resample both of them, so we have two sets of USET, we do the same thing, highlight them again, and attribute. And now we have our original USET and also our USET input one, which is basically the USET from our second slice. So if I get a second slice up, oh, that one. So it's identical to a second set. Or is it? Oh, right. Because okay. So the order that you highlight each actually matters. So because I highlight the bottom one first on slice two, that becomes our actual first U. So let's delete that and redo that. We sample first. And now hopefully our slice two or U input one is going to match up with our slice two. Voila. So it's worth double checking. But now we basically have the data from both plane into one, and we can easily use a part calculator. And let's say I want to do um, where is my huh? Oh right, okay. We did resample the image, so we only have point data now. So let's say U set minus U input one set, and we basically get a delta U set between the two planes. Um, Pretty powerful feature. You can probably do this almost as easy on Python as well, but this is an option. So I think that wraps up the second part of the series, and then the next part will just mostly look into parallel post processing, working in HPC, and if there's anything major that I've left or forgot, I'll squeeze them in as well. See you next time.